Hello again to all of my Applied Math Unit 1 students. I'm back. Today we're going to talk about populations and samples. Actually, I didn't realize that this topic is going to be this long. There are going to be 3 videos. One on populations and samples. The second video is going to be on random sampling techniques, and the third one will be on non-random sampling techniques, but they're all related to each other. But I've split it into 3 different videos. So here we go. Populations and samples. We're going to start with that. A population is a representation of a group or set of similar items or elements or people under consideration for a particular study. I've listed several examples of populations here. All the people currently alive that were born in a country, that's a population. That's actually a population of people, but then it doesn't have to be about people. The second one, this is about people as well. All students at a particular high school during an academic year. The third case, all the cars manufactured by a company in one day. Fourth example of a population, all the babies born at a particular hospital during a particular month. Populations are, I know I said mostly here, but I should say are sometimes dynamic. Populations are sometimes dynamic. What do I mean by that? Well, the population will not always be the same. New elements, let's say, are added to the population all the time, and sometimes elements drop out from the population. Classical example, let's look at my first example up there where it says the population is all the people currently alive that was born in a country. Currently alive. Okay. Well, that's clearly very dynamic because babies are born every day, so in that particular country they will be added to the population. People die every day, so people will be removed from the population. So that's clearly a case in which the population is dynamic. The sampling frame for that population would not be accurate at a particular point in time. We'll explain what sampling frame means a little later on. So they're sometimes dynamic. The second case, it's not that dynamic. The students at a particular high school during an academic year, maybe 1 or 2 students may drop out of school for that particular year. So that clearly is a case in which the population becomes a little less. And maybe 1 or 2 students are added, not at the beginning of the year, but maybe sometime after the academic year starts. But it's certainly not as dynamic as, let's say, the people in a particular country. So that's slightly dynamic. All the cars manufactured by a company in one day. Well, in any one particular day, that's clearly fixed. All the babies born at a particular hospital during a particular month. During a particular month, that's clearly fixed as well. Okay. From a population, we can do 2 things. We can take what's called a census, or we can take what's called a sample survey. A census is obtained when every member of the population is considered in your study. Right? Let's look at why we would need a census. A census is necessary. This is a classical example when a census is necessary. Census is necessary when a government is trying to document all of its citizens. This is tied directly into the first population I talked about, all the people currently alive that were born in a particular country. When a government is trying to document all of its citizens, you definitely want to have a census there to try to account for everyone in the population. Disadvantages, it's tedious and time consuming, and it's only done roughly every 10 years in most countries. Advantages, well, it's certainly tied to national security, right? You want to know that every person in the country, you want to be able to account for them, all of your citizens. A census, so that's when a census is necessary. It's definitely necessary when a government is trying to account for all of its citizens. A census is appropriate if a population is small, right? You definitely want to look at all the population elements when the sample is small. When the population, sorry, is small. Advantages: the results are accurate. Uh, my two favorite advantages: it's quick and it's cheap. There are no real disadvantages to taking a census when the population is small. A census is inappropriate if the population is large. Advantages? None really, unless you're taking a census of a country. Disadvantages: time consuming, costly, tedious, and it's very difficult for the results to be accurate for reasons that I mentioned earlier. Your items, sometimes some fall out of the population, sometimes new members are added to that population. And another very important disadvantage is a case in which the population elements are destroyed during the study. Right? I'll give my favorite example on that one just now. In fact, why don't I give it now? Because the rest, another part of the discussion will deal with a sample survey instead of a census. So what's my favorite example here? The disadvantage being, in some cases, the population elements are destroyed during the study. I always talk about this one. Most car manufacturing companies, in fact, all car manufacturing companies, they have to, after they have manufactured a new model of car, they have to test that car to see how it would behave under an accident scenario, crash test scenario. So you've probably seen it on TV where they would put the dummy in the car and they have a bunch of sensors on his head and neck and chest and so on. And so they put the dummy in the car and they would actually crash that car into a wall. And then they can get all the data from the sensors that they put there, airbag deployed correctly, and whatever other data that they collect from that. The main point of this discussion, though, is the crash test actually destroys the car. Now, if you made X number of cars in one day from your manufacturing company, do you want to carry out a census in your study? Do you want to take all the cars and test them under crash test conditions? I don't think so. So this is a classical case in which you definitely would not want to use an entire census. You probably want to take a sample survey where you take a small subset out of that population and you perform the test on that. And nice segue into what I'm about to talk about right now. A sample survey is obtained when a subset of the population is identified in the survey for consideration in the study. So you take a subset out of the entire population and you use that subset to perform your test. A sample survey is appropriate and desirable in most cases. Advantages: it's quick and cheap, my two favorite advantages. But actually, this third one is my favorite. Once a sample is representative of the population, it predicts the population characteristics with a great degree of accuracy. Right? To study a population, you do not have to study all of the population elements. You take a sample, a representative sample. Another name for that would be a random sample. Once you have a representative sample or a random sample, you are guaranteed that the results that you get from that sample, you can project it onto the population and conclude that that's the way the population is going to behave statistically. I think that's one of the most beautiful aspects of statistics. All right. So, by the way, let's look at some examples right here. You remember this? We studied this already. We studied point estimates. If we look at what I call sample statistics. X bar would be the mean for a sample. S squared would be the variance for a sample. And so let me actually make it obvious. X bar is called your sample mean. S squared is called your sample variance. And P sub S is called your sample proportion. You would remember that each one of those quantities has an equivalent notation in a population. When you're talking about the mean for a population, the symbol is mu. That's referred to as the population mean. When you're talking about the variance for a population, that's the population variance. And when you're talking about the population proportion, that's given by the letter P. Population proportion. There is a direct relationship between those two, the information from your sample and the values that you will associate with your population. We studied two types of estimates, you would remember. We studied point estimates and we studied interval estimates. If you wanted to estimate the mean for a population, mu hat, as shown right there, this is referred to as an estimate for the population mean. Who remembers what it is? Before I actually say it, I write it down. An estimate for the population mean. Let me move this out of the way. The estimate for the population mean is given by the symbol mu hat. And how do we estimate the population mean? We use the sample mean as an estimate. The second one is the estimate for the population variance. Estimate for the population variance. That's sigma squared, hat. You put the hat on it when you're trying to estimate the population value. The hat tells you it's an estimate for the population value. And it's more specifically referred to as a point estimate. Sigma squared hat is the estimate for the population variance. And that's given by n over n minus 1 times s squared, where n is the sample size. I know you remember that, right? N is the sample size. And how about the estimate for the population proportion? An estimate for the population proportion. P hat, yes, is given by P sub S, the sample proportion. I gave a very simple example for that third one, where in class what we did, we figured out the number of left-handers that we had in class. Y'all remember that little experiment? We didn't. You just had to put up your hand if you were left-handed. So it was nothing to figure out. We just counted the number of people who were left-handed. Out of, I think there were 20 people or 23 people in the class at the time, and I think 3 were left-handed. So the proportion of left-handers in that class was 3 over 23, whatever that is as a decimal. That was 0.13. And what I said, okay, go to school and take any one of your classes. That will be a population. Or take, let's say, for example, all of your sixth formers. Take all the sixth form students from any one of the schools. and figure out the number of left-handers in there. And you could be guaranteed that the proportion of left-handers in your entire class would be very close, not exactly the same, but very close to the proportion of left-handers that we had in our little class. So that was just a classical example in the way statistics work. We also talked about interval estimates. This is a good time to review some of these ideas. We talked about interval estimates. You remember we talked about interval estimates or confidence intervals, where we found an interval within which a population parameter, let's say for example the population mean, fell, and we would say, okay, the population parameter is within these limits, and we are 95% sure of that's the case, or we're 99% sure that that's the case. So that was one definition of a confidence interval or an interval estimate. Right? You calculate one interval with a left and a right boundary, and you say, for example, population mean, I think we did it for a population proportion, but let's talk about the population mean as an example. The population mean had to be within those intervals with a certain probability or a certain chance of being within there. There was a second definition for the confidence interval. A certain person is supposed to give me that definition, and I'm still waiting, but I know I'm going to get it. Let me give you the second definition here. If you were to take 100 samples out of your population and calculate a confidence interval, let's say you wanted to figure out what a 95% confidence interval meant. You take 100 samples out of your population, each of the same size, and you calculate a confidence interval for each of those samples. So now you have 100 confidence intervals. A 95% confidence interval would mean that 95 out of those 100 confidence intervals would have the true population mean within their boundaries. The other 5 would not. You would not know which 5 don't or which 95 do. You would just know that 95 of them have the true population mean within their limits, and 5 of them do not. All right, if we were to summarize this idea now, interval estimates and point estimates were therefore two ways of very accurately predicting population parameters. That was the gist of this entire discussion, right? That it fell onto the case where this third scenario here, where we said once a sample is representative of the population, it predicts the population characteristics with a great degree of accuracy. Okay. And then I gave a scenario where for a sample to be representative of a population, it must be random. It must be a random sample. Once we have calculated the sample statistics accurately, we can project this information onto the population to predict its behavior. I kind of said that before, but I just have it written down there. Okay, to obtain a sample, we must first identify each of the following. A, your target population. That's your population of interest, whatever you're interested in. B, your sampling unit. Sampling unit is an individual item to be sampled from that population. C, the sampling frame. Sampling frame would be a means of identifying all of the population items. And I gave 2 examples here. First example is, let's say my target population is all the public high schools in Guyana. My sampling unit would be a particular high school. A particular high school. And I just picked QC, Queens College. Just by chance. So one particular high school out of all the public high schools in Guyana, that would be a sampling unit. The sampling frame would be a list of all the public high schools in Guyana. And that list should be possessed by the Ministry of Education. They better have it. They better know. They better know how many high schools they have. Right? Target population, sampling unit, sampling frame. Here's the second example. My target population this time is all the pupils at a particular high school during an academic year. I pick Saints. Pick Saints this time. My sampling unit, a particular student, JL. Anybody got the initials of JL? I ain't calling no names. And my sampling frame, the school's register, most likely possessed by the headmistress. Again, she better have a list of all the people she got in the school, headmistress or headmaster. Right, so this concept of identifying your target population, your sampling unit, and your sampling frame, that's pretty straightforward. In above examples, the sampling frames are easily obtained and are accurate. Right. There are, however, many cases in which an accurate sampling frame is very difficult to obtain. The population or citizens of a country is a classical example of a sampling frame that is so dynamic that it is impossible to be accurate at any one instant. Well, we talked about that earlier, where we said the population of a country is extremely dynamic. People, you're trying to take a sense, you're trying to get a sampling frame for all of the people. People die, so they got to come off of the list. New babies are born, so they got to go onto the list. People can't be found. People don't want to be found. So it's a difficult task, especially if your country has a lot of people. I guess thankfully Guyana only has since I was a little boy here, Guyana only has 750,000 people. How many people they got now? I bet you all hearing the same thing. So for us, it's not that difficult. But in countries where the population is in the millions, that could be much more of an issue. All right, let's talk about bias. What is bias? Bias occurs when we are trying to obtain a sample and each sampling unit does not have an equal chance of being selected. Right? Bias, that would clearly be the case if you're going to use any one of the non-random sampling techniques that I'm going to talk about in the third video. Sources of bias: an inaccurate sampling frame. Right? People who should be on there are not on there, or people who should not be on there are still on there. That's an inaccurate sampling frame, and you have problems in trying to avoid bias. You're trying to get a random sample, so you're trying to avoid bias. Wrong choice of sampling unit. Bias introduced by the experimenter, and non-response from chosen sampling units. I'm sure you all have experienced some combination of the last two. You're doing your SBA or your project, your stats project, and let's say you have a questionnaire. So what's the first thing you'll do? I bet you the first thing you all will do is pass it out to your friends, like-minded individuals, instead of trying to find a random sample of people to pass it out to. Maybe some students from the lower school, maybe some of your friends, maybe a couple of teachers, maybe take some home. But if let's say you have 30 questionnaires or 50 questionnaires, you're probably gonna give it to all the students in your class. And then the next thing is your friend, quote unquote, quote friend, unquote. Sometimes they couldn't be bothered. So instead of looking at the questions and trying to accurately give you a response based on their observations, they're gonna circle A, B, A, C, A, right? Am I right? Y'all know I'm right. So in many cases, when you collect back those questionnaires, you really don't have an accurate idea of what the responses should have been. And bias clearly affects the accuracy of your results. So you want to avoid bias as much as possible. Okay, that's all I want to say for now about populations and samples, or censuses and sample surveys. Let's look at a question. And most of the questions, it's always a question one. They come in this format. I don't remember from which year, I think it's 2013. I took this question, or part of the question associated with what we just discussed, and we're going to go through it and see how well we can apply what we just learned to this question. A random sample of 25 students were taken from the fifth forms of a certain school in proportion to the number of students in each form. The data collected were classified as the following three variables. X, the variable X is the number of C6 subjects each student was studying, the number of subjects. Y was the favorite subject being studied, and Z was the distance each student traveled from home to school each day. The population of interest. Which one of those variables is the population of interest? What am I saying? Not which one of the variables. What is the population of interest? The population of interest would obviously be the fifth form students from a certain school. All fifth form students. From a certain school. A sampling method that was used to collect the data. All right, I haven't discussed this as yet. That's going to be in the next video, but I'm going to tell you what it is right now. It's actually called stratified random sampling. It's called stratified random sampling. And we'll discuss the details in the next video. The variable which is qualitative. Well, variables are usually can be broken up into qualitative variables and quantitative variables. Quantitative variables can be described using numbers. So if you look at X, the number of C6 students, that's quantitative. Z, the distance each student travels, that's also quantitative. Y, your favorite subject, that's clearly a quality, and it's therefore a qualitative variable. So the variable that is qualitative, that will be Y. The variable which is continuous. Now, quantitative variables, let me draw a little flow chart here. Give me a little space. Okay, yes. Variables can be broken up into qualitative and quantitative. Quantitative variables can further be broken up into discrete and continuous. A discrete variable would be one in which you can only use whole number values to represent it. A continuous variable would be one in which you can only represent it within a given range or to a certain degree of accuracy, to a certain number of decimal places. So when they're asking for the variable which is continuous, well, there are two variables that are quantitative, and one would be discrete and one would be continuous. The continuous one would be the distance each student has to travel from home to school each day. So that would be Z. Right? 12.5 miles, or 2.63 miles, or whatever the case is. And then the variable which is discrete, well, that would be the one that's, you can use a whole number to represent it. The number of C6 subjects each student was studying. You're either studying for 10 subjects or 12 subjects or 15 subjects, a whole number. You can't study for 12 and a half subjects. I don't want to see one of y'all do that. So the number of C6 subjects studied, that would be X. Okay. There's one other problem. I decided to stitch it in here because I'm not going to do an entire video just for this. This particular topic, we didn't cover it as yet, but we're going to cover it now. And it has to do with, okay, it has to do with, let me get my bearings here, excuse me. It's called coding. And we kind of did it, but we didn't refer to it as coding. I'll show you what I mean. So I'm going to look at this problem right here. A sample of 36 data values gives sigma x minus 45 is equal to minus 148. Sigma x minus 45 all squared gives 3089. Calculate estimates for the mean. So they want the mean of x. That's the first part. Well, there are 36 data values. And the mean of x, I'll start by doing that. Mean of x bar, is equal to sigma x upon n. But we don't have sigma x directly. We have sigma x minus 45. So one good way to deal with this is to code the x minus 45 and call it a new variable. So here's what I'm going to do. I'm going to let x minus 45, I call that y. Let y be equal to x minus 45. So those two expressions up there will become sigma y is equal to minus 148, and sigma y squared is equal to 3089, right? Okay. And then I'm going to find the mean of y. Y bar is equal to sigma y upon n, where n, by the way, is, they told me I have 36 data values. Oops, y bar, not x bar. Y bar is equal to sigma y upon n. Sigma y is minus 148. N is 36. Minus 148 over 36. Uh, 4.113 sig fig. But I'll keep this guy, the full value, because I might need it later on. So, well, in fact, forget about 4.11 because I really don't need y bar. I need x bar. The question is y bar related to x bar? Well, let's see. You would remember we discussed expected values? Expected values when we were doing probability distributions. Expected values and means are basically the same thing. If we have, which we do, y is equal to x minus 45, then it means that the expected value of y is equal to the expected value of x minus 45, which is expected value of x, and the expected value of a constant is that constant. Right? Let me write it back here. Expected value of y is equal to the expected value of x minus 45. Well, what do you think expected value means? This expected value of y is y bar. Expected value of x is x bar minus 45. And therefore, if I want x bar would be equal to y bar plus 45. If I change this up, I get that formula. Therefore, x bar, the mean of x, is equal to y bar, which is minus 148 upon 36, plus 45. That's 148. Plus 45, which gives me 40.89. Good. So calculate estimates for the mean. Just did that. I'm sure what you mean by estimates. It's an estimate. Calculate the estimates. Why do you keep saying estimates? Calculate the estimate for standard deviation. Okay, well, we're going to say y bar. Sorry, sy squared is equal to sigma y squared upon n minus minus y bar all squared. So therefore, sy squared is equal to sigma y squared is 3089 upon n, which is 36, minus y bar. I'll actually put in the minus 148 upon 36 all squared. $84.02. And therefore SY, standard deviation for Y, is equal to 9.17. Y'all should check my numbers back. 9.17. I think I'm right though. But that's the standard deviation for Y. I want the standard deviation for X. Well, not a problem. Because what do we know? We know that Y is equal to X minus 45. And var Y, variance of Y, is equal to the variance of X minus 45. Which means the variance of Y is equal to the variance of X, and the variance of a constant is 0. So variance of Y is the same as variance of X. So sy squared is equal to sx squared. Variance of Y is variance of X. If you square root both sides, you get the variance of X. Variance of Y being the same as the variance of X. What's my conclusion there, therefore? Therefore, Sx, which is what I really want, the standard deviation for X, is 9.17. Yeah, y'all please double check my numbers. Let me actually double check this one though. Okay. Yeah, that looks good. That looks good. 9.17. Right. All right. So that's that. The last part here deals with what is it asking for? Another data value x equal 29 was added. Calculate the values of the mean and standard deviation of the 37 values. Okay, no problem. Because we know if another data value is added, now we have 37 data values to deal with. The old x bar was given by sigma x upon n. We know x bar because we just calculated it, 40.89 is equal to sigma x. Remember, they didn't give us sigma x, they gave us sigma y. They already gave us sigma x minus 45. So from this, sigma x, 40.89 is sigma x over 36. So if I cross multiply there, I'm going to get an expression for sigma, a value for sigma x. Sigma x would be equal to 40.89 times 36. What does this give me? $1472.04. What? $1472.04. Okay. 1472.04. And therefore, now the new x bar new would have to be the sum of all the 36 values, 1472.04, plus the new number that I added in, which is 29, and divide that now by 37. And divide that now by 37, and you get 40.57. Okay. How do I now find the new standard deviation? Here's the standard deviation. 40.57. And you would expect the mean to go down because the old mean was 40.89. You added a value that is less than the average. So it makes sense that the mean went down. Yes, let's see what the new standard deviation is. We know that sy squared is sum of y squared upon n minus y bar, right? All squared. And we know sy squared was 84.02 is equal to sigma y squared, which is the number we're trying to get, divided by 36 minus y bar, which is 9.17 all squared. So let me see if I can calculate what sigma y squared. This would be plus times 36. Ooh, big number. Sigma y squared, 6051.92. Now, why did I need sigma y squared? Because the new sigma y squared will be sigma y squared will be 6051.92 plus 29 squared. By the way, I would have to calculate a new y bar, right? That should be easy to do. Yes, that would be 6892.92. Okay, and now that I know the sigma y squared nu, sy squared nu would be equal to sigma y squared nu upon n in this case is 37, minus y bar nu. But the new y bar, remember x and y are still related by the same variables. If you go back up here, I have it somewhere. Y bar is x bar minus 45. Y bar is x bar minus 45. So that would be 40.59 minus 45. And this is squared, by the way. Y bar is 40.57 minus 45. Which gives me minus 4.43. And therefore, if I plug into this guy, I get sy squared nu is equal to 6892.92 upon 37 minus into minus 4.43 all squared. Minus and if I square root that, I will get 12.9 for just y, the new y, sy is equal to 12.9. But the standard deviation for x is the same as the standard deviation for y. So sx is also 12.9. What was the old standard deviation? 9.17. All right. I have a feeling I have to check over these numbers. If anything, if I have, I probably don't have to make any corrections, but if I do, I'll do it in the next video. All right, I'm going to stop this video right here. End the video. What do you know? All right, the next two videos, like I said, will deal with random sampling techniques and non-random sampling techniques. All right, I'm out for this one.